Welcome, everybody. Looks like everybody is here. Could you turn your video on, please? Great. If we cannot see each other personally, this way we can watch each other through the internet. That's great. So you already got my mail, and hopefully you watched every movie that I asked for watching it, okay? Yes, any question before we start the presentations and the first lesson?
I have a question.
Okay,
Sorry.
let's go step by step, okay?
So I was added into your group this morning. I didn't know anything about your group, so I apologize in advance because I haven't received any material from you. I was wondering where can I send my email so that I receive the same material as well?
Okay, one possibility, you can send it through the chat privately to me, and I can add you to the list of my group. So, okay, let's see, participants, fine. Okay, please write your name and email address as well. And I will give you.
Okay, thank you.
Okay, yep, all right, I already get it. Wow, there are more than only one. Okay, let's see. All right, so this is one. Hopefully I will figure out. Okay, come on. Somehow it doesn't want to work. That's not good. Wow, so many chat messages. Jesus Christ. Okay. Oh boy. I have the same situation. Okay. But why cannot I? Yes, I can copy it. Okay. Good. All right. What? All right. I'm sorry, but it takes a little time. Okay. Copy. No. Oh boy. Somehow I cannot copy it. I don't know why. Maybe I'm going to write it. Sophie. That. I'm sorry it takes time, but okay. All right, so let's see, Sophie is there. Okay, Chusuho is there. Diana, no, the Diana is next one.
Maybe we can just share with them the docs that you send and they just can add it themselves.
That's true, but I need this email address as well. And of course, that should be very nice if you share them, the documents. It doesn't take too long. Okay. I'm sorry. Okay, this is Yahoo again. Okay, Lena. So many students joined to this group.
Somebody just sent a Google document. Is it okay if we just all add our email address to that?
Yeah, that would be very nice. Yeah,
Yeah,
that would be
okay.
very nice. Okay, thank you very much. That would be very nice. Okay, I already put 1, 2, 3, 4, 5 email addresses, but that's the Google one. Google Docs would be fine. Okay, now.
And also something small, I have been having that issue. I don't know if anyone else has been having it. The PDF files that are put on Moodle, which are like tracing workbook, explanatory pages, and tracings, they kind of have a password. So I can't add them to like my iPad so that I can write on it.
Okay, let's see. So first of all, you want to have ECG and the tracings, and you say that this tracing has a password.
Yes.
Oh boy. Okay, let's see. Okay, this is. Huh. It's only one problem. I do not see anything that you do have any password on it. I don't know why.
That's the thing. When I download it on my laptop myself, I can open it, but when I try to import it into like the application that I can take notes on it, it says it needs a password.
I didn't put any password on the PDF file. Believe me.
Oh, okay.
I have no idea what happened. Sorry, but any purpose, I didn't put any password on it. So sorry to say, but no. You mean that the iPad, I don't know what kind of application you are using, but I will try it. What application that you are using for iPad? Making notes.
I'm using GoodNotes.
GoodNotes. Okay, I check it. Okay.
Yeah, okay.
GoodNotes. Okay.
Thank you.
You're welcome. Anything? Lina?
I've been having problems with the registration for ECG. So I emailed my registrar to register me for this group or another group that is on this day because all the other classes overlap with my schedule. So is it okay to attend this class now so I don't have an absence later?
Okay, that's fine. It's no problem. Yes, you can attend it. That's okay. All right. Officially, this group or this class starting at 8 a.m. And I ask you to start this lesson today and the next week, but we don't need to start on the next week at 1 o'clock. We can start at 8 a.m. if you wish. 8 a.m. is good for everybody?
Yeah, I loved it.
Okay.
Yes.
Good. So 8 a.m. All right.
Excuse me. Like
Yes?
for me and Mao, it doesn't work because we are having the class like microbiology from 8. That I emailed you before.
Yeah, I know. With Zoom, yes, everybody with Zoom. Okay, so at 1 o'clock would be fine to everybody.
Yes.
Okay, let's stick to 1 o'clock. We can do it at 1 o'clock. Okay. Anybody wants to protest again this 1 o'clock, 1 p.m.?
1 o'clock until
7.
when is it? Just
1 at 2:30.
Oh, okay. Yeah, it works for me.
Okay, 2:30, and we do have officially
Can we
starting.
do 12, if anyone don't mind it?
It's no problem. 12 o'clock.
Yeah, 12 is better for me as well.
Okay, 12 o'clock. Who's for everybody? Okay, 12 o'clock.
So how about the 12:10? Because I'm sorry, because my schedule is just messed up. So Mao and me, I was like, I have a class like statistics till 11:50.
Okay. We are starting at 12 o'clock and you can join 12:10. All right. During the 10 minutes, nothing happening, and you can watch back because we are recording these lessons and everything. So if you miss the 10 minutes, it's no problem. You can watch it. All right.
Okay, yeah, thank you so much.
So 12 o'clock every Thursday. Okay. Good. It looks like we handled everything so far. All right. So who has any question? Who watched the videos, at least the first introductory videos? Good. Any question? No question. Okay, first of all, I have to ask question, and after you will have zillions of questions for sure. Okay, so every week we do deal with the different topics. At the first week, that's an easy one relatively, because only generally introductory period, what you learn in physiology, this be identical, what the ECG for, and only the practical view, two things that we have to do it. Basically, we have to describe an ECG tracing. I think it would be very nice if we start showing it, and after I will say, who is the first one who has the 101 videos? Well, not videos, the PDF form, the tracing. Who has it? Okay, please share your screen with that tracing. All right, almost. Okay, great. Okay, good, very good. So first of all, when you start evaluating an ECG, it doesn't matter what kind of ECG you are facing with, the first thing you have to look at the paper, the recordings. What you will first see without knowing anything, the rhythmicity. You can judge whether the RRR intervals are equal or not. You do not need to count in millimeters. Only what you have to do it, look at it, and very similarly when you're entering in the room and looking at the pictures on the wall, and you do see that, for example, this one is rhythmic. Now, this is one thing. After, yes, very nicely, it's written that regular rhythms, very good one. After that, we have to calculate the heart rate. Okay, how do we calculate the heart rate? I'm not saying anything. Now the presenter is going to show us how she calculated the heart rate. It's written. Okay, we cannot hear you. I think you have to unmute yourself.
It's
Yes.
not noisy. Sorry, I'm in school. Hello.
Yes, we hear you.
Yeah. Oh, that's good. First of all, I used the old way when I use in the physiology. So I calculated with counting the small boxes as well. But once I watched the video, you mentioned about the big boxes with the 300 rules. So if I use the big box divided by 5, which is 5 boxes between the 2 peaks, I got 60 beats per minute. So that's the estimate heart rate.
Okay, very good.
Okay.
Now, you do not need to be so accurate, because it doesn't matter whether the heart rate is 60, 65, or 70. So this way you can estimate by, okay, for example, guessing it. Now here you say that you do have 5 small squares. Let's see. I think you do not see my cursor. Can you give me your cursor? If you go up, and you can see that share the cursors or anything, or the remote controls or something like that, you can do it. Or in the middle one, all the way up, and on the right side, you do see a cursor and saying that remote control. Okay, it's no problem. If you cannot give me it, it's okay. We will learn later on how can we do it. Okay, now let's look at, for example, the tracings, lead number 1. Now, if you do count how many big boxes you have between 2 Rs, you do see that 1, 2, 3, 4, not exactly 5, a little bit less than 5. It's meaning that if you had 5, that should be 60. But because it's less than 5, it's a little bit more than 60, so you can guess it's about 65. Doesn't matter. If we had 4, 300 divided by 4 is 75. So if you between 4 and 5, you can guess on the row, it means about 15 beats, and you can judge whether the 4 is closer to the 4 or closer to the 5, and you can guess what could be the heart rate. This is one thing. Another one, I think it's better one if I if I'm going to share my screen and showing the tracing, and that would be nicer one, I think. Let's see. Yes, it's right here. Okay, good. All right. Now you can see my cursors, and this way that's a much better one. Okay, so this is what I said. Okay, less than 5. Okay, this is one thing. When you do have rhythmicity, you can use this calculation very nicely. However, another one that very similarly, when you feel the pulse, you're saying that, okay, you are calculating the bits, the pulse within, let's say, 15 seconds or 30 seconds. If have a longer period, you can be more accurate one. But on ECG, you cannot use this one because you cannot count for half minute or 1 minute or maybe 15 seconds. But you do see, for example, here, that means, okay, this is 1 second. You do see a little teeny tiny darker dots here. So 5 boxes means 25 millimeters, exactly 1 second. This is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and 6 seconds. Okay, very good. Let's count how many R's we have within 6 seconds. 1, 2, 3, 4, 5, 6, 7. And you have to multiply by 10 because you are interested in 60 seconds. So it's meaning the average heart rate around 70. It does not matter because the heart rate changing. And we say that the normal heart rate is between 60 and 100. Of course, if you do have an internal medicine course, they're saying that it should be 60 and 90 or 80 or something like that at the rest. But because the rate is depending on age as well, an elderly patient usually has a slower rate and younger one has a faster rate. So this is how you calculate it. So by meaning that you count for 6 seconds, you have to multiply by 10. However, if you count to 5 seconds, as we see, 1, 2, 3, 4, 5, 6, you have to multiply by 12. If you multiply by 12, now you do see that's about 72. All right, you can count for 1, 2, 3, 4 seconds. If you count for 4 seconds, you have to multiply by 15, makes it to 60. So it means 1, 2, 3, 4, 60. See, you are right. If you count only for 1, 2, 3 seconds, you have to multiply by 20. So this way you can guess the heart rate very easily. If you don't remember or you cannot count, let's see, you cannot divide 300 by the number, it's easy one. Let's count for 1 second, 2 seconds, 3 seconds, 4 seconds, and you can count the average rate. Now this will work when you do not have a normal regular rhythm. Okay, good. All right, let's go back. I'm going back to you the screen. This was one thing that you figure out, the heart rate. That's relatively easy one. The next one, we do, oh, everything is written there. Okay, next one, we should look at how the tracing looks like. Do we have a P wave in front of the QRSs? Now that's be the second lesson because it's meaning that we want to determine where the impulse is formed, whether this is originated from the atrium or from the sinus. Mostly the sinus generates the impulse, and it's meaning that the P wave always found in front of the QRS complexes. Okay, yes, we do have a P wave, for example, here very nicely. Now, we don't know, but regularly the PR interval that we are dealing when the conduction abnormality is coming one, but let's see the PR interval, and she already calculated that this is in the normal range, fine. So it's meaning that it's completely fine. The PR is not this one. Okay, that's good, very good. And let's see, enlarge it, because that's not good that you've written here. Because what is the PR interval? The PR interval starts at the beginning of the P wave, yes, from there to the beginning of the QRS complexes, right there. And if you count how many boxes you have, 1, 2, 3, 4, it's meaning about 0.16 seconds. See? And that's completely normal because you said that was very nicely 0.12 to 0.2 seconds. So don't forget the PR interval includes the P wave, okay? The PR distance is starting from the end of the P till the beginning of the QRS, and of course, it's shorter one. But the PR interval, it's always start at the beginning of the P, okay? Now, next one is the QRS complex that we have to describe it. Of course, later on, when we're dealing with the morphology of the P wave, for example, that you already learned it because it was in introduction that, okay, the P wave should fit in the 1/4 of a big boxes. So it's meaning the duration is 0.1 second and the amplitude cannot be bigger than 2.5 millimeters, but it's fine. When we talk about hypertrophy, we will discuss it, don't worry about it. So the morphology of the P is okay. QRS. Next in a QRS, first of all, we have to look at the width of the QRS, how wide the QRS complex is. And the normal interval is up to, I would say, up to 1 second, not longer than 1 second. And if you do have a wider one, of course, something happens inside the ventricle, maybe conduction abnormalities, maybe from a different area, the impulse is formed. But this QRS is narrow. We can say that QRS is narrow, normal. Now here, we can calculate the axis. Why do we need to calculate the axis? Now, why do we need this axis? Tell me, Sarah.
Why do we calculate the axis?
Yeah, why do we need this axis? Because that's so strange and somebody should fail you on this axis and that's just completely not understandable thing. So what do you think? Why the axis is important?
To estimate the location of the heart?
Yeah, but I can use an ultrasound, I can use an X-ray, I can use more proper, let's see, technique to evaluate how the heart is placed in the chest. I don't think so. And basically the anatomical axis and the electrical axis is not the same. Close to each other normally, but not the same. So I don't care about how your heart is placed in your chest. I can look at it, you looks very nicely, so I don't care how your heart is placed. But, no? What is a normal axis? What is a normal main electrical axis? What is the main electrical axis?
Mean of the electrical axis? Main electrical axis? Main electrical axis.
Okay, so it's meaning that during the ventricle activation, of course, you always do have a little vector. And if you summarize this vector, that gives you the electrical axis. So it's meaning that what could be the sum of these little vectors? What is a normal electrical axis?
You mean the degree of it or?
Yes. Yeah.
0 to 90?
Okay, exactly. 0 to 90. Well, it's a very big range. Very, very big range. So, so if it's between 0 and 90, we don't care about it because that can be normal. And basically, if you are younger one, it's closer to 90. If you're an older one, and maybe you have a big belly, it's closer to 0. So why do we need to calculate the axis? Because
maybe it's like you mentioned, when you get older.
No,
I can look at
your ID.
Try to get a hint.
Okay, no, we want to see the pathological condition, it meaning that when the anatomical axis or the anatomic situation cannot explain the axis deviation. So we want to see what are those pathological conditions when the electrical axis cannot, let's see, explain based on the anatomical situation. So it's meaning that we want to see and we want to make a diagnosis, because if the electrical axis doesn't give you back the anatomical axis, it's meaning that during the ventricle activation, the electrical impulse formation was abnormal. So this is why relatively, we want to see the pathological condition. Now, which are those pathological conditions that the anatomic situation cannot explain the axis? We said 0 to 90 was the normal one. On the left side, for sure, this is one is 0 to 90. Let's go to the left side. If it's less than minus 30, so between minus 30 and minus 90, that for sure it cannot be explained as an anatomic situation. So that's called extreme left deviation or pathological left deviation. And of course, we can make a diagnosis out of this one. That can be due to hypertrophy. That can be due to, for example, different blocks, hemiblocks, for example, or left bundle branch block. A lot of things that can cause this pathological left deviation. On the other side, the right side. What could be the extreme right deviation? It's over 100. It's overdone. Okay, if it's all more than 100, or wait a minute, I ask, let's see, I leave it right there. I want to get to this point when I can give you, I think, right there. Okay. Okay, yes, almost, don't give up. Yes, it's right here. I'm sharing. Again, I'm sharing. Good. Let's share this axis. Okay, so that was the extreme left deviation when it's over minus 30 to minus 90. And we do have an extreme right deviation when it's over 110, for example. So this situation cannot explain due to any kind of anatomical situation. However, we do have another area, such as, for example, between 0 and minus 30. This area is called left deviation. What does it mean? It could be normal, but could be abnormal as well. For example, if an obese or pregnant person, for example, comes and you do see that the deviation is minus 10, for example, or close to 0, or a little bit less than 0, that can explain based on anatomic situation, because the belly pushed up the heart diaphragm, and this way the heart is placed horizontally. Another thing, if somebody is young one, teeny tiny and tall one, that can be over 90. But if you do see a guy who is fat, big belly, and you do see that 100, for example, degrees, for sure, it's not possible to have an anatomical situation such as this one, because the heart is placed horizontally. That could be due to, for example, right ventricle hypertrophy or any other things that can cause a right deviation. So this is why we are using this axis, determine the axis, because we want to make a diagnosis. We have to explain it. When you describe an ECG, you have to explain why the patient has an extreme left deviation or extreme right deviation. You do not need to explain what the normal is, all right? But this case, okay. Now let's go back to your picture. So let's see, how do we calculate the axis? Almost. Yes. Now, how do we calculate the axis? How did you calculate the axis?
Since I didn't have any Equivalency Qrs Complex on my ECG, I used the Quadratic Approach.
Okay.
And since I got positive I and positive AVF, he says that's a normal axis.
Exactly. That's very good. That's very good.
you.
This is why you do not be so accurate one. So first of all, you have to look at lead number 1. Lead number 1 is positive. It's meaning that you are on the left side. Okay, well, after I will explain you. And when you look at the AVF, if it's positive, for sure, these two quadrant, it's only one thing, between 0 and 90. So that's a completely normal axis. That's it, period. You do not need to be accurate. But of course, maybe during the midterm or during the exam, they are asking you. So let's go further. Now, how can you narrow down this axis?
How did I narrow down the axis?
You said there is no equiphasic lead.
Oh,
but,
yes.
But if you look at lead number 3, can you look at lead number 3? Sometimes it's positive, sometimes it's negative, sometimes positive, sometimes equiphasic. Why this axis is changing?
I don't know.
Yes, you know it, you know it, you know it.
I knew something wrong, but I cannot really explain how is
and
it.
Anybody can
turning
explain what can cause the changes of the axis that comes regularly? Okay, I help you. Take a deep breath. Exhale. Do you think that the diaphragm is not moving? And when the diaphragm is moving, your heart is moving. So the axis is moving all the time. In every revolution, it can be different one. It's depending on the position of the heart. And anatomically, if you, for example, take a deep breath, the diaphragm is going down. So basically, the axis a little bit placed further down toward the right side. When you exhale, the diaphragm is moving back. Again, you can be a little bit more horizontal. And in this case, you can see very nicely whether it is positive or negative because exactly the axis is perpendicular to lead number 3. And what is lead number 3? Lead number 3 is 120 degrees. You have to come back 90 degrees. Okay, it meaning that the axis is around 30 degrees. Yes? Sarah?
Sorry, I don't get this.
Okay,
so
now I show it. Okay, I show it. Okay, let's go here. Let's go here. All right. This is a quadratic approach, but let's see. I don't want the quadratic approach, but I think equiphasic approach. Okay. Okay. I'm sharing it now. So what the equiphasic approach says, you do have an equiphasic, so the positivity and negativity of the QRS is equal. It meaning that there is no, let's see, or 0, the sum of the positivity and negativity is 0. So it's meaning you are exactly perpendicular to that lead. Okay, now let's look at which is perpendicular. For example, there is an example right here. Here you do see this equiphasic is AVF. Yes? Okay. It meaning that in AVF, equiphasic, so AVF is sum of this, let's say vector is 0. So it can be 0 or can be 180. There are only 2 possibilities when you do see nothing in one lead. This is okay so far, because the vector reflection or the generated, let's say, potential difference is proportional to the cosinus alpha of the angle of the vector and the measurements, or the, let's say, this probe. So we do see 90 degrees. Okay, we go here or go there. Now let's see in your case, I think that's a tracing. This is lead number 1 tracing. Okay, this is yours. So it meaning that you do see equiphasic to lead number 3. Okay, what is lead number 3? Lead number 3 is 120. So let's see, 90 degrees is 30 or 210. We have to choose this way or that way. Is it on the positive range or the left side or on the right side? Okay, let's look at lead number 1. Lead number 1 is positive. So it's meaning that you are here. So the axis is plus 30. Okay. Now, if
why did we look at lead number 1?
Because lead number 1 is positive on the left side. So everything is positive when the impulse goes toward lead number 1. Okay.
But I thought we should look at the lead that is perpendicular to the one that
Doesn't
has
matter, doesn't matter, doesn't matter. This is another possibility. You can use another approach. Which lead you do see the highest deflection, highest positivity? Because it's meaning that you are parallel to that lead. That's it. If you do see the highest one at lead number 2, it's meaning the axis is close to 60. If you have a highest one in lead number 1, it's close to 0. This is one possibility. Or you are searching for a 0 when you do not see anything. If you do not see anything, because the positivity and negativity are about the same, because you have to calculate the underlying area during the ventricular activation. So this is why the positivity and negativity should be summarized. If the QRS is narrow, if the QRS is not narrow, it's basically this cannot be used because the integrated areas should be used to calculate the axis. For example, let's see, look at this one. Which is the highest one? Well, relatively you cannot choose because lead number 1 and lead number 2 are about the same. When can you have the same reflection in lead number 2 and lead number 1? If the axis is exactly in the middle, because the reflection should be equal in these two leads. That's it. You can use this one. But generally talking, this quadratic approach, look at lead number 1, look at AVF, because if you use this quadratic approach, okay, it's meaning that you are here between 0 and 90. That should be normal. That's it. Okay.
Can I ask about the definition of equiphasic again, please?
Okay, the equiphasic means that the positivity and the negativity should be equal. That's an equiphasic one. Equiphasic, for example, if you see nothing, that's an equiphasic as well. But if you look at this is positive and negativity, but a little bit more positive than negative. This is not equiphasic. However, here it's more negative than positive. Negative, negative, and positive. This is why the sum of this all could be about the same, so it's about equiphasic. Here, what I showed you, this very nicely, you can see the equiphasic lead right here, say AVF, because the positivity and the negativity about the same. So if you summarize how many millimeters, we have about 1 to 2.5, and all the way down about 2.5. So this is why is equal, because positive 2.5 and negative 2.5 is means 0. So this is why this AVF is 0. So, and this is what means that, okay, 0 or 180, but let's look at lead number 1 is positive. If lead number 1 is positive, you are on the left side, so that has to be 0. Okay. All
so
right.
we can consider the whole
yes
QRS complex, not only the one complex.
Exactly, because you have to calculate the whole QRS complex, because you are interested during the ventricular activation that you have to summarize the momentum vectors. So the whole vector should be when the whole heart is depolarized, the ventricle is depolarized, and that heart can use somehow substitute only with one vector, and that could be the main electrical axis. Okay. All right. Let's see the next one, 102.
I have a question.
Okay, for sure.
So in the equiphasic approach, like concept-wise, why do we look at lead 1, and then if that one is positive, we choose that axis for lead 3?
Okay, all right. Let's go here and let's explain you very nicely. Okay, I already said this one, but let's look at this. Okay, let's look at this one. Okay, equiphasic one. Let's look at 1, 2, 3, and AVR, AVL, AVF. Only we are using the frontal panel. We are not using the horizontal panel because the horizontal panel, it won't influence the frontal one because that's 90 degrees, so there's nothing. And the axis usually we want to see in the frontal panel, so only these 6 leads can be used to determine the axis. Okay, let's look at lead number 1 is positive, yes? Lead number 2 is, well, positive, but if you get closer.
Don't see your screen.
Are we
Oh,
supposed to
I'm
see your screen
sorry,
exactly?
I'm sorry. Yes, I did not share. Okay, now you do see it, okay?
Yeah.
Okay, so what you do see here, that, can you see it? Can you see my screen?
Yes.
Good.
Yes.
So in lead number 1 is positive, yes, very nicely. Lead number 2 is, well, a little bit more positive than negative, but it's close to 0. If you summarize the positivity and the negativity, it's almost 0. Okay, so it's meaning that we do have a equiphasic lead is lead number 2. Okay, so what does it mean when we do have an equiphasic lead in lead number 2? It means that lead number 2 is 0, so you have to come back 90 degrees here and 90 degrees up. So 60 plus 90 means 120. 60 minus 90, of course, that's 60, that's minus 30. Okay, so these two, because 90 degrees that you have to come back. Now the next one, whether this is minus 30 or 150. If you are on the left side, minus 30. If you are on the right side, 150. Which lead will give you, whether you are on the left side or right side? Lead number 1, because lead number 1 is positive on the left side and negative on the right side. So this is why you look at, for example, lead number 1 or AVL, doesn't matter because both on the left side, and to see that 1 is positive, so you are somewhere here. Okay. All right.
Yeah. I think I got it. Thank you.
Okay, but don't worry, it takes time and you have to be used to it. So that's another thing. Okay.
Just a small question. When we say left or right, are we talking about like the vector that is pointing,
Yes.
like the mean vector? Okay.
Main electrical axis. This is what we are saying. During the all activation, all the ventricle, I think, oops, I closed it. That's great. That's great. I think, okay. Somehow I have to get back to this point where I can get to these areas. Okay, so, oh, nope. Yes, it's right here. Okay, so when you calculate the main electrical axis.
Could you share your screen?
Yes,
again?
I'm going to share it. I found it.
Okay.
That's be great. Okay. Yes. So during the ventricle activation, this is the sum of this little momentum vector that you have it. In every second, you do have a different dipole during the activation, and you have to summarize, and that's give you the main electrical axis. Okay, this is what we want to see. We don't need to see the one, or let's say the momentum vectors, but if you summarize it, it's relatively during the activation, this momentum vectors has a circular or loop, and that loop, when you summarize it, that gives you this main electrical axis. Okay. Now, who has 102?
Normally it's me, but I haven't had the time to do it. So
okay, let's do it together. Can you see my screen on this 102?
I see it.
Okay, now, what is the first one? Rhythmicity. What do you think? Is this rhythmic or not?
Yes, it's rhythmic.
Good, that's rhythmic. What about the heart rate?
The heart rate, I would say it's around 60 BPM.
Okay, that's about 60 beats per minute. Well, you can use about 1, 2, 3, 4, 5, so close to 60. Okay, or you can use 1, 2, 3, 4, 1, 2, 3, 4, 60. That's good.
Mm-hmm.
We do have a P wave. Yes, it's okay. Fine, the PR is okay. Normal, the QRS is narrow. Now let's see the axis.
Mm-hmm.
Let's try to find the equiphasic lead where the positivity and negativity are about the same.
Is the first one lead one?
Exactly. First one. What does it mean when we do have the first one? I go right there.
Axis can be 0?
No, the axis cannot be 0 because it's meaning that at lead number 1, you have 0. So it has to be 90 degrees to lead number 1.
Okay. So
Exactly. So it can be minus 90 or plus 90. Okay. So minus 90 or plus 90. Which one that you look at? AVF. Because
positive.
AVF is all the way down. AVF is positive. That means 90. AVF is negative, minus 90. And here, AVF is positive. So that means that's a 90 degrees.
Okay.
Okay. Good. 103. Who has 103?
I have it.
Good. Do you want to share your screen or let's leave to
I
mine?
didn't write anything, so
Good.
yours
So
is
this
fine.
way you can do it. Okay.
So it's rhythmic.
Mm-hmm.
The heart rate is around 120.
Okay, very good. So it means that less than 3, but more than 2. So it's between 100 and 150.
I counted how many
That's
QRS
great.
are in 3 seconds.
That's good. 1, 2, 3, 1, 2, 3, 4, 5, 6, 120 because you have to multiply by 20. Good, very good. Okay.
And both lead 1 and AVF are positive, so it's a normal axis.
Very good. Now, do we have any equiphasic lead?
No.
Oh, how can we estimate the, let's see the axis.
What was your question again?
How can we estimate or tell me, how can you tell me the exact or axis? No? Which one that I suggested you? Look at which is the biggest one. 1,
So
2, 3, 2. So it's meaning it's close to 60. Yes? So it's meaning it's close to 60. But if you do have 60, it's meaning that should be equal deflection in lead number 1 and lead number 3 because 60 exactly in the middle of this one. Yes? 60, 60. Did you follow me?
Can you say that again? I didn't understand this part.
Okay. 60 means, lead number 2 means 60 degrees. Lead number 1 means 0. Lead number 3 means 120. If you had 60, you are equally placed from 0 and from 120. And because lead number 1 a little bit bigger than lead number 2, lead number 3, it's meaning that you are a little bit closer to lead number 1. But lead number 3 is still positive. Lead number 3 is equiphasic to 30. Yes? So if you had a 0 or equiphasic in lead number 3, that could be 30. But because it's positive, it's meaning the axis is between 60 and 30. So you can say 40, 45, doesn't matter. By only judging that lead number 2 is the biggest one, after lead number 1, and later on lead number 3, it has to be somewhere here. Because lead number 1, This is the biggest one. So of course, it's on this side. If you had on this side, lead number 3 should be negative, and lead number 1 should be bigger than lead number 2.
So if lead number 3 would be negative, then we would be between 0 and 30.
Yes, but in that case, lead number 2 should be less than lead number 1.
Why
Because-
would it be negative again? If lead number 3 was
If lead number 3 is negative, meaning that this is 0, lead number 3 is 0 at 30, and negative on this side.
okay.
Because that's 0, 90 degrees. If it's more than 90 degrees, it should be negative. Positive on this side, negative on that side. You always have this 90 degrees. This is a quadrant approach. That's another possibility how you can calculate it. Now, you will practice, don't worry. This looks like it's very difficult, but believe me, this is the easiest part of the ECG. Okay, 104. Who has 104? Nobody?
Yeah, I have it for 104.
Okay.
Wait a second. I'm trying to, like, how do I say?
Share your
My
screen.
screen?
Share
Yeah.
it. Share it.
Is it on? Can you see my
Yes.
screen?
Yes. But
Okay.
now you have to choose the tracing.
Yeah, I did it as I can according to physiology that I had last year.
Okay, good. So first of all, rhythmicity.
It is kind of rhythmic because, like, for the first time, it is kind of longer, but as then it is same about for 4 small block boxes.
Okay, that looks like is not exactly rhythmic as you expected, but however, you do see that somehow the distance between the first and the second one is longer than maybe in the middle one, but that could be due to the respiration. This is what we are going to learn when we do have an impulse formation abnormality. Okay, but that's okay. That's normal. Okay, let's go on.
So I calculated for the heart rate, it is about 71.4. So
oh,
it can
Jesus
be said
Christ.
as normal.
70, that's around 70. Never
Yeah.
calculate the heart rate is, let's see, with digits or 2 digits or so. It's 70 is more than enough. But doesn't matter if 72, 75 or 70 or 69. Nobody cares about it. Okay.
Yeah. And then as you can see here, like I did it the average from the each segments.
Oh, Jesus.
The PR segment was the, like, in the average number, which was 0.12.
Normal.
Yeah, but the QRS was kind of a bit longer than the normal since it was 0.144.
Well, a little bit when you place the little squares at the end of the QRS complex, but this is not the end of the QRS complex, a little bit less. So you do see the J point that is coming. We will learn it later on. At least one square should be less. So if you do see that it's a little bit less than that one that you are expecting, so that's a normal one. Believe me, that's a normal. It's not wider.
Okay. Yeah, then the one that I wrote below here is kind of like, it doesn't really count then. But the significance that I can see is that there was no ST segment.
We don't care about ST segment yet. I want to see the axis, axis.
It's the one that I didn't wrote. Like,
That's be very similar to the previous one, which is Acrophysic lead. Acrophysic, when the positivity and negativity are about the same, that lead number 1. Yes. And look at AVF. Look at AVF.
AVF?
Yes, AVF is Positive. So it means
Positive.
that you do have a 90 degrees.
Okay.
It's identical to the previous one.
Mm-hmm.
Okay. Good.
Okay.
Next one, 105. Who has 105?
105 me.
Okay. Share your screen, please. I can share mine if you wish. Okay, that's great.
지금 되고 있어? Okay. No.
I can share mine.
This one.
Okay, great. Okay, now let's see.
I did the two approach, the quadrant approach and the Acrophysic approach. First of all, for the
Can you take
approach,
my video out of this tracing somehow?
Oh.
Yes, thank you very much. Okay.
So, according to the manual, I first saw the first LED, and it is a positive, so it is left.
Before you go to the axis, rhythmicity, heart rate, okay?
Oh, actually, I don't know, even it is rhythmic because the first and second one is a little bit different. Because I think it's because the respiration.
It's no, it's not. Because if you're looking at, let's see, the different bits, you do see that some bits may be a little bit further each other, but you can point which bit is closer to another one, okay? For example, this is the first, second, third, fourth, fifth. The fifth one is very short or very close to the previous one. And if you're looking at another list, you do see that they are not rhythmic. You can say it's not rhythmic. We do not need to judge what caused this arrhythmia, but it looks like it's not a regular rhythm. So how can you calculate the heart rate when you do see this kind of arrhythmia? The average, yes.
Average, yeah.
How can you average the heart rate? As I suggested you should count for a longer interval, okay? You can count for 4 seconds or 3 seconds here.
Yes, and so
how many? 1 second, 2 seconds, 3 seconds, 4 seconds. Okay, how many beats you have during 4 seconds?
1, 2, 3, 4, 5, 6.
6. Okay, 4 seconds we have 6. It means that if you want to see how many you have 60 seconds, you have to multiply by 15.
Yeah.
So it means
so it's
90. Okay, so that's 90. So the average rate is 90. It's still in a normal range. Okay?
Yes.
All right.
Okay.
Now you can go for an axis.
So first of all, I saw the first LED, and it's positive, so it can be located in left. And next, I saw the AVF, and it's negative, so we can see. We have to see the second LED, whether it is left deviation or extreme left deviation. So if you see second one, it's almost equiphasic, but it's a little bit positive. So we can say it's left deviation, but in this point, I applied the Equivalency approach. So it's, and also we can see AVL, it is very positive. So I thought it's almost equal to the AVL. So in this, I draw this point 0 to minus 30
Very good,
degree.
very good, very good. It's not exactly minus 30 because lead number 2 a little bit more positive. So this means a little bit less than minus 30. You can say minus 20. Doesn't matter. It's a left deviation as you've written there very nicely. That can be normal or can be pathological. Okay?
Okay.
Good.
Can you please explain again how she did the axis?
Okay. Or she can explain first of all. Let's see, how can she explain? And after I try to explain if you cannot follow her. But
Explain
my
about what?
picture
Sorry.
should be taken from there.
Sorry.
Okay.
So what was the question? Sorry.
How did you estimate the heart rate? This is what she asked.
Not the heart rate, the axis.
No, I mean the axis. I'm sorry. I wanted to say
just
the
like
axis.
the exact like range of the angles.
So I did first the quadrant approach, and you know it's between the 0 to minus 90. And then through the second leg, we can know whether it is left deviation or extreme left deviation, but it shows a slight positivity. So it will be 0 to minus 30. But
okay, that's okay. I explain her again. All right, that's okay. You did it very nicely. You did it very nicely, but now you are using the quadratic approach. Okay, this is a quadratic approach that we are using it. Okay, what this quadratic approach says. I'm sharing my screen right away. Okay. Okay, good. So the quadratic approach says that one lead is positive in a range of 180. Half circle is positive, half circle is negative. As I said, lead number 1 is positive from AVF till minus 90 and negative on the other side. So positive on the left side, negative on the right side, okay? If you look at the same time, AVF is positive down and negative on the up half. Yes? Now, you should combine these two. Let's combine it, saying that one is positive, so you are on the left side. But AVF is positive. It's only this quadrant is true for both, between 0 and 90. Okay? However, in our case, when we had here, one was positive. Okay, that's good, very nice, because meaning we are on the left side. Let's look at AVF. Negative, meaning that we are somewhere here because we are on the left side. This is on the right side of AVF, but the right side is not true because lead number 1 was positive. So you are located between 0 and minus 90. This is okay so far. Huh?
Yes.
Okay.
It's
now,
okay.
But this means 90 degrees is too much. We want to see whether it is pathological or not. So which lead is going to be perpendicular to minus 30? Lead number 2. Okay, let's look at lead number 2. Lead number 2 is almost equiphasic. So immediately you can say that it's minus 30. But look at this. This is a little bit more positive than negative. So this is why she said that between minus 30 and 0, so we do have a left deviation, not a pathological left deviation, only a left deviation. Okay?
Yes.
But you can do the same by the equiphasic approach. Lead number 2 is almost equiphasic. Okay, if lead number 2 is almost equiphasic, it meaning that minus 30 or 150. Let's look at AVL. AVL is positive. Well, AVL is positive, so it meaning that's around minus 30. But because it's not exactly negative, let's say equiphasic lead number 2, but a little bit positive, you are coming back about 10 degrees or 5 degrees, doesn't matter. So this is less than minus 30. So this is not an extreme left deviation. Okay.
Okay, thank you.
Okay, let's see. 106.
It's me.
Okay.
Can I share the screen?
Oh, I'm sorry.
Okay, no problem.
Yes.
Can you see my screen?
It's going on. Yes, it's almost. Yes. Okay.
Okay, so first of all, for the heart rate.
First of all, the rhythmicity. Rhythmicity is the most important.
Okay, so this I think is irregular in this case.
I don't think so.
Oh, really?
I don't think so. That is rhythmic. Look at the RR intervals. It's changing. The first RR interval, maybe this a little bit less than the second one and less than a third one. It's shorter, one shorter. This is not rhythmic at all.
I said not rhythmic. I said it's
irregular. Okay, that's
yes.
good. Irregular.
Okay,
That's
irregular.
fine.
Okay,
okay,
so,
good.
I counted for 4 seconds. And I could count 10 times in 4 seconds. So we multiply 15 to 10 and we can get about 150 BPMs.
Terrific, terrific. Okay, go on.
And I've seen the waves, but I couldn't actually see the P waves.
Well, we will learn it later on where can you see the P wave, mostly lead number 2 or V1, but it's not the meaning, not the impulse formation abnormality that we are dealing with, but it looks like it lead number V1. For example, V1, if you go down, possible you do see P wave, but this piece is different, one is not the same. So in the next, we will learn it, what does it mean, but doesn't matter. It's not a sinus for sure, because there is not very nice P wave located in lead number 2. Okay, go on.
Okay.
The axis,
So
this is what we are calculating today.
Okay, so as we see, the lead number 1 shows positive. And so I checked the lead AVF, which is also showing positive, which means you can know that this hard electrical axis is in a normal axis. And to specify the angle, first of all, we can see number 3 as equiphasic, because
yes,
I don't know about the behind part like this.
That's
but
okay. Again,
yeah.
changing the axis to the breathing. Okay, go on.
Okay, so as you know, number 3 is equiphasic. It means it should be perpendicular to the number 3 axis, which means it's going to be near 30 degrees.
Exactly. That's about 30 degrees. Very good. And if you look at lead number 1 and lead number 2, lead number 1 is bigger than lead number 2. This is why a little bit less than 30 degrees. So I would assume that lead number 3 a little bit more negative than positive. So it's meaning about 20 degrees. That's okay. Still in a normal range. Still a normal range. Okay, good. Very good.
Thank you.
Very good. Okay, now we go and look at 107. Wow. Who has 107? Nobody. Looks like nobody has 107. I will share my screen.
Can I try?
Try, yes.
Yeah, because I'm really, yeah.
Try it. It's yours.
Oh, okay, okay.
It's not the nicest one, but it's okay. You can go for it.
So it's definitely not rhythmic because you can see it. And heart rate, we have 6 beats in 5 seconds.
Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. I would say 7.
Or about 7. So it would be 7 times 12.
Okay.
Which would be
84.
84.
Okay.
Yeah, about 84. And about the axis. So a quick question, how can we how do we choose whether we do the quadrant approach or the equiphasic, like whether we can see equiphasic waves or not, or?
Okay, if you do see equiphasic one, you do not need to use the quadrant approach. If you do not see any equiphasic one, you can use the quadratic approach. Now here, for example, the quadratic approach is the nicest one because you can see whether it's pathologic or not. Look at lead number 1 and AVF, both one positive, so that's in a normal range for sure. However, you do not see a very tall R wave, so it looks like it's a small R that you do have here. Okay, look at this AVL. Look at AVL. AVL is close to, oops, oh, wait. Sometimes it does work, sometimes it does not. It's about equiphasic, see? AVL is equiphasic one. AVL is minus 30. Now you have to go back, minus 30, minus 90, it means about 60, AV, lead number 2. Or you add, it meaning that minus 30 plus 90, it's meaning that you are on the next right side, 270. So for sure is not because lead number 1 is positive. So this means that you have second lead, so it means 60. And if you look at lead number 2, this is about the biggest one. It's about, let's see, 3 and 1 about the same. So you can see this is about 60 degrees. Almost.
Can you say that again? I didn't quite understand how you got to the 60 degrees.
Okay. AVL is equiphasic, okay? AVL is equiphasic. What does it mean? 60 or 240? Because 90, 90. Lead number 1 is positive, so this is why you are somewhere here. So this is why is 60. Okay? But if you go, which is the biggest one? 1, 2, 3. Well, 1, 2, 3, maybe 1, 2 is the biggest one because there is no negative part of the QRS complex in lead number 2. But in lead number 1 and in lead number 3, you do have negativity and positivity, and about the same as if you compare 3 and 1. So this is why it's 60, because it's exactly in the middle. But this equiphasic lead AVL shows that yes, it has to be lead number 2. Okay.
I can't understand something.
Yes. Okay, now what?
After you chose the equiphasic lead, then how do you choose which one to look at that direction? Because sometimes you choose one, but in your videos you said to choose the one perpendicular. So
no, first
it's a bit confusing.
Okay. This is perpendicular. We said that lead number AVL is equiphasic. Okay, so we are somewhere here. It's meaning that we are exactly 0. So you have to come back 90 degrees or add 90 degrees, because these two will give you a reflection at AVL 0. But you don't know whether this is lead number 2 or 240. Look at what is lead number 2, positive or negative. If it's positive, you are here. If it's negative, you are there. Lead number 2 is positive, so it's meaning that it's about 60.
Okay, thank you.
Okay. 108, who has 108?
Yes, it's me.
Okay.
Could you share screen? Because I wrote everything down on my iPad.
Yes, you can do it.
Oh no, I meant, could you share your screen?
Yeah, it was shared.
I'm gonna use my iPad.
Okay, it was shared. I wanted. Okay, now let's see.
Yeah,
okay.
This is the rhythmic part, like rhythmic one.
You want to zoom it to where?
To the left upper side. Yes, this side, and then just a moment, please.
It's okay.
And then heart rate, like there is a 3 heartbeat within the 3 seconds. So it means like there is a 60 beat per minute.
Okay, it's rhythmic or not? It's rhythmic or not? This is the first thing that you have to ask.
I would say rhythmic.
Is this rhythmic?
I'm not sure because there is a big gap between the first chord.
Okay, this is rhythmic. This is not. See? The rhythmic? No.
Okay. So
it's not rhythmic. This is irregular. It doesn't come in the regular time. Okay.
yes, yes.
Okay, go on.
And then I count the heart rate. And then the answer, it's around 60 beat per minute.
Okay, can be. Okay, good.
Can I
All right.
connect to the axis? And then I choose the first lead because like it seems there is no equiphasic one.
Okay, there's no equiphasic one, but one is the smallest one, yes?
Yes, it's because like according to your video, like you started with the like number like one lead. So
lead number one is positive, AVF is?
And then AVF is also positive. So the axis is located within the normal axis range, which is like
but how much? Let's see, how much? Can you narrow down?
When I check the read number three, and it is positive. So I also draw that line on the figure. And then, so if I sum up with all the results, and it says like it is axis located within the 60 to 90.
Okay, that's very good. Exactly, between 60 and 90. Okay, that's very good. But look at which is the biggest one. 1, 2, 3. 2. Yes, 2 is the biggest one. So it's
close
almost,
to 60.
exactly close to 60. And after lead number 1 is smaller than lead number 3, so it's meaning it's over 60. So you are between 60 and 90. That's it.
Yeah.
Yeah. Congratulations. That's great.
How did we come to the fact that we're between 60 and 90 again? Could you repeat that?
Let's look at. She said that lead number 1 is the smallest one. Yes. Okay, lead number 1, if it's the smallest one, it's meaning that it should be 90 or minus 90. Okay. Look at AVF. AVF is positive, so this means this around 90. However, lead number 1 is still positive. So it cannot be 90, it should be less than 90. So this is why she said that's between 60 and 90.
Okay.
But if you follow the following one, which is the biggest one? Lead number 2. After you have to compare lead number 1 and lead number 3. Which is bigger? Lead number 3. So you are somewhere here, but lead number 1 is still positive. So you are on the left side. It cannot be on the right side. So this is why we got to the conclusion that between 60 and 90.
Okay. Okay, got it. Thank you.
Okay. Now let's see the 109.
It's me.
Okay. You want to share your screen?
Yes.
Good.
While she's sharing her screen, I was just wondering, the PDF that you're using, is it possible, is that available
Yes,
to
I
us?
will send you the link where you can download this PDF form, okay? And
okay, thank you so much.
You're welcome. Okay, now?
I'm trying to
share
screen. No, this is
not yet.
Not yet.
No?
No.
I will share my screen, and after you can guide me, okay?
Okay.
Now, let's see.
So
Rhythmicity, heart rate, axis.
first the heart rate, it's not rhythmic.
Yes. Now,
So
in this case, for example, this is a little bit different ECG that you do see, because in some lead you have only 3, or sometimes you have only 1 beat. But you do see a rhythm strip when it's a longer interval, and you can calculate the heart rate and look at the rhythmicity right here. And this is lead number 2, what you do see here. This is what she said, it's irregular. Good, very good. Okay, what?
I counted the number of R, and it was 7 R waves within 6 seconds. So 7 times 10
70
is 70. So 7.
Hey, I can count. Good.
BPM.
Okay. All right. Go on.
Then next one is axis. D2 has equiphasic Qrs complex. So I look at ABL, and then it's positive. So minus 30 degrees.
Good. Exactly. Minus 30. But it's a lead number 2 is a little bit more positive than negative if you look at it. It meaning that a little bit less than minus 30. I mean, it's a little bit more than minus 30. This is minus 20. So this is a left deviation. Yes?
Yes.
Okay. Good. Very good. 110.
In this,
yes, go
in 109, could we also go through saying like lead 2 is equiphasic, and then go through that method as well? Yeah. Okay.
You can use it the same. Yeah.
Okay. Thank you.
Here you can go for it, a quadratic approach. One is positive, AVF, whereas AVF is negative. So you are on the upper part of the left side. Look at lead number 2. Lead number 2 is not negative. So you are not an extreme left deviation. This is only a left deviation. That's it.
Okay. Thank you.
110. Who has 110? If nobody, somebody should do it. Who wants to do it?
I can try, but I'm not. Oh,
do you hear me?
Yes.
Okay. And first, the rhythmicity. I would say it's irregular, right?
This is regular or irregular?
I didn't know, because there are.
Okay, you have to look at the distance between the R's, and I think they are same.
Yeah.
But this is bradycardic for sure, because it's a very long distance between these two R's. So it's regular, but the rate is?
Like it's very slow.
Okay.
And there are 5 R waves within 10 seconds, so it's gonna be 30.
Good, very good. So the heart rate is 30 beats per minute. Okay, very good.
And heart axis. And lead 1 looks equiphasic, but I didn't know if it is, so
yes, it's okay. Yeah, they're good. Very good, very good. This looks like lead number 1 is equiphasic. Okay, that you can see this positivity and negative are the same, but I would say that a little bit maybe more positive than negative, but you can assume that that's equiphasic. Okay, which is another lead that you have to look at when one is equiphasic.
So I didn't know if it is equiphasic, so I used Quadratic Approach to get precise angle. And first the lead 3 and lead AVR, and the lead 3 is positive and AVR is negative. So the axis is going to be between 30 and 120 degrees.
Well, I don't know why you went that way, because if you look at this equiphasic approach, lead number 1 is equiphasic, so it means it's 0. It has to be 90 or minus 90.
It's quadrant approach. It's not.
Okay, quadrant approach. Lead number 1, relatively, it doesn't show you anything because this is 0. Yes?
Yeah.
Okay. You can choose AVF. Okay, let's choose AVF. Okay, AVF, I go for the quadrant, it's positive.
Yeah, it's positive. So it's going to be between.
This is between 0 and minus 90. I mean, not 90, whatever is the quadratic approach, another side, 180. Okay, so we are somewhere here.
Yes.
Okay. Now, the next one that you can use, which one that you want to use, doesn't matter. You can use this half circle. Use lead number 3. You use lead number 3.
AVL.
AVL.
AVR.
AVR. Okay, AVR is negative. AVR is negative. It meaning that you are somewhere here. So it meaning that you are between 0 and 120.
Yes.
Okay, it's still a big range. Okay, which is the next one that you want to narrow down?
AVL.
AVL, okay, AVL is negative. Okay, AVL is negative. It meaning somewhere you are here. Yes. Okay, so it meaning that you are between 90 and 60. If you want to use this quadratic approach, you can use it. You can use, for example, color pencil and color that half that is positive or negative. And whichever has the most color, the axis is there. So always when you're taking the half circle, everything, whatever you said, should be true. And only one area is true. But if you do see an equiphasic lead, do not use the quadratic approach because you know exactly what the axis is. This is one. Lead number 1 is, let's say, equiphasic. So this should be perpendicular to lead number 1. AVF is positive, exactly 90 degrees. You don't need to use this quadratic approach, but if you wish, doesn't matter, use it.
Okay, thank you.
So it's close to 90 for sure. But if you said between 90 and 60, that's okay. So usually about 30 degrees you can narrow down, but that's a normal axis for sure. Okay, that's it. We don't have more. We have only 10, yes? And the next time I'm going to share you more videos about the impulse formation. Now that's be more difficult than this regular axis and heart rate. Of course, you always have to know the axis and the heart rate, but now we add some abnormality when the impulse is not formed in the normal areas. And this is what we're discussing. So I'm going to send you a link for those materials that you have to watch. And of course, you will get similar ECG tracing. And now everybody is going to get that tracings and their own tracing. If you don't worry. Usually I said that ECG is very simple one, but for the first glance, it looks like that is very, very difficult. Now, maybe you are feeling that, okay, that's okay, because something that you already learned in physiology, that's not a big deal to know that maybe the axis is the biggest problem right here, not the heart rate. But believe me, that's be the smallest problem. We are approaching, let's see, the jungle. In the next week, we are reaching the jungle. If you confuse so far, you be confused much more, believe me. And when we have the conduction abnormalities, it looks like you are inside the swamp and you cover by a big sheet and you won't see anything. And when, let's see, the ischemic heart disease comes, oh, Jesus Christ, let's forget about ECGs and everything, the life. I'm not being a physician, but don't worry. By the end, you can describe any kind of ECG tracing. Doesn't matter what kind of tracings you will get, you can diagnose it. This is why we always practice. I give you a lot of tracings, and I share you those PDF forms as well about what the video made of. And you be a good expert on ECG. If you go anywhere in the world, believe me, you will feel that, your knowledge is more than the other graduate student in overseas, or maybe in England, or maybe in France or other areas. Believe me, because this is what they said. Whoever went in an Erasmus student there or something, believe me, you will know everything. So don't give up. Only keep watching the videos and try to describe your ECGs that you are getting. The midterm that we do have, for the tracings for the midterm is be similar or identical that we already discussing. I'm not giving you, let's see, a completely unknown ECG. Believe me, you will face hundreds of ECG by the time, because always we are getting and combining the knowledge that we have to know by the end of these 7 weeks, okay? All right, guys. So next week, 12 o'clock.
Just regarding the issue I told you in the beginning, can I share my screen with you to describe it? If anyone wants to
please, it's okay. Everybody's interested in what you want to say.
Okay, so basically the problem that I had is this. Let me just get okay, share screen. So
Professor?